So let's go back to the flow against the wall example. So remember, we were given a velocity field that looked like this, v0 over L times minus xi hat plus yj hat. This is a steady 2D flow. I know it's steady because there's nothing that shows up in time here. And what we're asked to do is, given a known velocity field, let's find the acceleration field. And while we're at it, let's separate out the local acceleration and the convective acceleration. So first off, we're just going to tap into the definition again. The acceleration is defined as the substantial derivative with respect to time of the velocity. Remember, that substantial derivative is just applying the chain rule to the fact that the velocity is a function of time and space. And so when we do this, we get the partial of the velocity vector with respect to time, but we also get these extra terms, a u dv dx plus v dv dy plus w dv dz. And the first thing we're going to do is apply our steady assumption, which says we can cross out time derivatives. There's that one, that's the steady. And this already actually answers part of our question, right? The local acceleration is that time derivative. And so we can right away just write out the, whoa, what have I done to my pencil? Oy. We want to be writing with a pencil. And so we want the local acceleration, a local, is just equal to 0. So that's actually the second part of our question, but we answered it along the way here. In addition, it's 2D, which means we don't need to account for anything in the z direction. So I'm going to get rid of this term here, 2D. And so what we'll be left with then is u dv dx plus v dv dy. And so now it's just a matter more or less of plugging and chugging. Remember that u is the x component of the velocity without the unit vector attached to it. Ditto, v is the y component of the velocity vector without the j on there. And so let's grab ourselves a u. It's going to be minus v0 over L times x. And that's getting multiplied by dv dx. So we're going to take d by dx of the entire velocity vector, which is v0 over L. We got a minus x I hat and a plus y j hat, the whole thing. And we're going to add to that v dv dy. So v is the y component of this, which is going to be a v0 y over L. So we distribute that through. And then d by dy of the entire vector, which is written right here. I'm going to scroll down so we can see it easier. Again, this is a derivative of the entire velocity vector, v0 over L times minus x I hat plus y j hat. So there we've subbed it in. Now it's just a matter of following the math through. So let's take a look here at the first term. Leave this alone for a minute. That's just v0 over L times x. And then we want to take the derivative of what's inside here. Well, d by dy, that's, or dy dx, that's a 0. So the only thing we care about is right here. And dx by dx is just a 1. And so we'll be left with v0, oh, not an x, v0 over L. Over L. That minus sign is going to stick around, as is an I hat. And you know, just for clarity, let me go back and put it inside these parentheses so you can track what came together. v0 over I hat there. Okay. And now we're going to do the same thing here. We got this part stays alone, so v0 y over L. And now we're going to apply this derivative. dx dy, that's a 0, so the whole first term goes to 0. d by dy of y is just a 1. And so we'll be left with v0 over L times j hat. And so we can multiply some things through and simplify this a bit and discover that our acceleration is equal to v0 squared over L squared times x I hat. That's the first term. And then the second term looks like v0 squared times y over L squared times j hat. So that's our overall, that's our total acceleration vector, the whole thing. Because it's steady, the time derivative portion has disappeared, and so this turns out to answer both parts of the question. This is the acceleration, and it is the convective acceleration as well.